Today we're going to talk about electric motors and propellers. We'll first get into some of the theory explanation about how these work, and ultimately the goal will be to help you choose an appropriate motor and propeller. If you go look at these databases, there'll be lots of motors, lots of propellers, and different battery options. We want to try to find a good combination that's going to work for you. So we'll get into this today, again, mostly with sort of some understanding and theory, and next time a little more into some of the matching that goes into this. So let's first talk about DC motors, the direct current motor. Many of your household appliances and all sorts of things, I shouldn't say appliances, gadgets and things will have a DC motor in them. Many electric vehicles and the airplanes that you'll be building will use these as well. So let's try to get a basic understanding. We're not going to go into too much depth, but try to understand basically how this works. One key idea is, well, let me draw a magnet here. So we're going to have a magnet. These will be permanent magnets. Say here's a north pole, a south pole. This is going to be, let's say a side. I don't know if we should call this the side or the top. So this is a side view here, okay, of a motor. And we're going to have an armature that's going to come in. This is going to be a wire. It's going to come in. Let's just draw something like this. Okay, and then this is the direction of the current. It's coming in here, comes around, and then out. Okay, so there's a current passing through this wire. Call this the armature. And the magnetic field goes from north to south, creates a magnetic field in the direction as shown by the blue arrow. Erase this side here, sorry, that's in the way. And we'll call this B. That's a normal symbol for a magnetic field. So if I have this current moving through a magnetic field, you may remember that this is going to create a force. This is a Lorentz force. So in the motor, this part is fixed. These are permanent magnets. And this current moving through a wire creates what's called an electromagnet. And this current moving through this magnetic field is going to experience a force, the Lorentz force. Read this way, differential force is going to be the current times a length along the wire crossed into the magnetic field, B. Okay, DL is just a length. If it makes it easier, let's just make it right like this. Let's just make it simple. We'll call current. Normally we don't call current a vector, but just to make it simple here, we'll give it a vector. Normally it's the length that we go along the wire, but conceptually it's not really that different. So here's my motor, and let me give a, I don't know which side to call this. This is side view. Let's say this is like a top or a back view. So this would be as if I was viewing it from this side here, right? So I'm looking this way. That's my eye. I'm going to look at it this way. So I'm going to see the wire. Here's the wires. And these are the magnets. Right? So the magnetic field is still this way, but the wires are now going into the page. Okay, so that's just a second view. If we look at this cross product, this force, so as this current moves through this magnetic field, so we put our hand, I'm looking at the top one, let's look at this side of the wire first. So it's going up and the magnetic field's going to the right. So I'm going to take my right hand, crossing the right. My thumb is now pointing into the page. So there's this force into the page here. Okay, so that would be on this view down, right? So this is kind of that back view down. And then on the other side of the wire, right, so the current is now coming around to the right. So I put my hand going down that way, cross, magnetic field's going to the right, so across the right. My thumb is pointing out of the page. So on this side, there's a force that's coming out. And so from this view, that would go up. And that means here's this axis here, right? And so there's this axis here out of the page. And that means that force is going to cause this to rotate. So those permanent magnets in blue, those are fixed. Those aren't moving, but that inner part is around a shaft that can freely rotate. So that armature is going to rotate, right? Because of that current, that force is determined by the Lorentz force is going to rotate until it gets all the way to the other side. When it gets to the other side, it's going to stop because now both the currents have flipped direction. There's no, the force isn't going to want it to keep going any further. So what we're going to do, let's think about it this way. Imagine that we replace this electromagnet with just a regular magnet. I'm going to draw this and erase it. So let's say I had a permanent magnet here that originally looked like this. North was here and south was here. So they're going to be repelled. If I perturb this just a little bit, it's going to rotate and it's going to want to spin around until it hits the other side, right? So it's going to spin around and it's going to stop there. We want this to keep spinning though, right? So if I could spin this, get this started, spin it around, and then I could reverse those magnets, I could get it to keep going, right? And keep going to spin around and around. That's going to be hard with these permanent magnets. I can't get the permanent magnet to just flip signs. So to repeat what I was saying here, I've got this north-south thing in the middle. It wants to rotate, and if I could get it, once it rotated over to flip signs, so that now south and north flip, I could get it to continue to go. And if I kept flipping it around, I could get it to rotate and rotate and rotate continuously. Okay, that's hard, of course, with a permanent magnet, but an electromagnetic magnet, I could do that. I could get the current to switch direction. So if I switch direction, everything here would switch. So once I flipped it around, now the current on this side would be coming towards me, but then I'd flip it so I get the same picture here, and the rotation would continue. Right, so I want it to flip direction every time it goes around, flip the current around. So to do that with an electromagnet, I don't want to just I can't just tell it to flip. So what I'm going to do is I'm going to create, let's see, how am I going to draw this? I'll create what's called a commutator. And this is a nice thing about electromagnet, right? As opposed to permanent magnets, that we can reverse this direction. So do this with a commutator. Let's continue on this back view here. So here's this back view. I've got these wires going in. And let's say I've got this, I'm going to draw it as just two pieces, but that's generally not how it's going to be. I've got these two pieces, and then I've got these brushes here. Okay, so this is going to be the brush. This is the commutator. And so in this case, let's say the current comes in here and it leaves out this way. Okay, it's really going, sorry, through these brushings here, this way and out this way. Okay, and so as this commutator comes around and I switch, there's a little gap here. As I switch and I get from one to the other, then I can reverse the direction that the current is traveling. Sorry, this commutator, it's coming into these commutators here, coming in and out this way. So I can change the in and out side as this moves around, and that's going to switch the direction of my current. So basically, you think of this magnet here, right? It's repelled, it wants to rotate around, and as soon as I get around, the current switches, so the direction of that magnetic field, or the force changes, so it keeps spinning, and then I switch again as I get around, keep spinning, and so it's going to keep spinning round and round. Now you can imagine if we use our magnet analogy, right? I've got these fixed magnets, and I've got this one magnet here that's repelled. It comes around, stops, we switch it, it's repelled. Right? That's kind of jerky, right? It's going to slow down as it comes around. So to do this more efficiently, there's several things we do. First, from this side view here, we're going to have these kind of curved permanent magnets. And then we're basically going to use the same principle here. If I've got this back view, here's this wire, right, that's coming into the page and coming around, but I'm just going to keep doing that again and again. Let's just draw like 6 of them here, or 3 pairs, right? So I'm going to have more of them. And then I've got this commutator, and I can switch it and break it up into many pieces here. And so then instead of just having like one repulsion and traction, I could say at this instance, have this one, these pairs, and this is the opposite, right? This one is going to be attracting this one, and this is going to be repulsing this one, and I just keep switching that around as I go around. So because of that changing in the current, I get this force, this Lorentz force is going to cause me to rotate. And so I basically converted an electric energy here into a mechanical, I should say really power is what we're after, mechanical power. The other thing that we're going to have to keep in mind here, well, actually, let's continue with this here, this train of thought. So what we've got going on is that we've got a current that's moving through here, and it's going to generate a torque. And from this equation, we saw it generates a force, but I just add another, this moment arm here, right, R, and this is F. So R cross F is a moment. So I've generated this torque here. We can see that torque is going to be proportional to my magnetic field and my current. Generally, I don't want to get into the details of the magnetic field for my motor. So at this high level, we're going to use a simple model. We're just going to say that the torque, we can see it's proportional to the current, right? The torque, Q, is proportional to the current. Sometimes you may see tau. We're going to use Q because that's what aerodynamicists use for torque, and we're going to connect this to propellers later. So we're just going to use Q, but you may have seen tau in another class. Okay, so the torque is proportional to the current. If we wanted something more exact, right, we can work it out from the magnetic field, but we don't want to do that. In this case, we're just going to do a higher level motor model and wrap all the constants for the magnetic field, such in this proportionality constant. Proportionality constant we're going to call KT, and it's going to be multiplied by the current. To be more exact, we're going to subtract what's called the no load current. And this just accounts for, some friction in the windings and such. So I drew this with one wire. Normally, it's more efficient to have many wires, so you'll see many wires wrapped around in that same direction. But there's some internal resistance here. If I put just a tiny bit of current, I'm not necessarily going to get a torque. There's a little bit of this no load current I have to overcome, small number, before I get an appreciable torque. But conceptually, if you don't want to worry about that, we can just say the torque here is proportional to the current, and that's just coming from this Lorentz force here. Okay, so this is one element of the problem. Another thing that's going on, though, what to be aware of, and again, we're just going to discuss this at a high level, is the back EMF. So now if I've got this wire here, it is now moving downwards. So I've got a current moving in a magnetic field. And a current moving in a magnetic field experiences a voltage drop. This is called the back EMF. It's an induced, or you could call it, this is from Faraday's law of induction. So this is an induced voltage. As a current moves through a magnetic field, it induces a voltage. We call this a back EMF in a motor. It's also called an induced EMF. And so conceptually, you could think of this as this is the voltage drop that is occurring across the motor. Right? I'm not going to get this for free. I'm going to lose some voltage potential across the motor. And it is related to, running out of room here, so I'm just going to go to the next page here. This is Faraday's law. You don't really have to know this. This is just some background here if you're interested. So this voltage drop, this is my back EMF, is going to be equal to negative times n, that's the number of windings, and the change in my magnetic flux per time. And magnetic flux is B dot dA, it's an integral of B dot dA. So basically, if you think of, I've got this cross-sectional area that points this way, and the magnetic field points this way, right? So it's just a dot product between them. So if we go back to this picture here, I've got this magnetic field that's going this way here, right? There's B. And as this thing rotates around, that area that's that current is, the area that magnetic flux is going through is changing in time, right? So the magnetic field in this case isn't actually changing. We have a constant magnetic field, but the direction that area is facing is changing in time. So that's going to create this voltage drop. Okay, and again, if those details didn't make sense, we're going to again back it out to a high level. So from this equation here, I'm going to call this the voltage across the motor. That's the back EMF, but this is for our motor. It's going to be proportional to to what? Well, it's this area that's changing in time. So how does that area changing in time? Well, that's changing in time because we're rotating. So it's going to be proportional to that rotation speed. If I rotate faster, then that magnetic field, this flux here, is going to change faster in time. And there's going to be some proportionality constant, right? Depending on the number of windings, the magnetic field. At this high level of the motor, I don't want to worry about those details. I just say that that voltage is proportional to that magnetic field. And we call this proportionality constant, depending which way to write it. I'm gonna write it the other way. This is more typical. Let's say omega is proportional to, this is called kV as a motor constant. Okay, so this motor constant, we just call it kV. It's typically given in units of RPMs per volt. So you can see this is a rotation, could be in RPMs. This is a voltage, some volts. So if I divided that over, units for kV are often given in RPMs per volts. Just be careful with that. That can be tricky sometimes because, you know, for these units, later when we combine things, sometimes you want the units to be radians per second. That's going to be more our standard SI units. So rotations per minute, you may have to convert, but just to note that when you look up motors online, you'll often see it in RPMs per volts, and you'll probably have to convert it at some point to radians per second per volts. Okay, so now we have this equation. We've got how the rotation is related to the voltage drop across the motor. We've got how the torque is related to the current. I'm not going to prove this, but we can show from an energy argument that 1 over kV, that these two constants are just inverses of each other. Okay, so if I've got this equation here, and I'm going to take this equation from before. I'm going to write in terms of kV. So we've got Q equals 1 over kV times I minus I naught. Okay, so I need to put these things together, and the way we'll do that is just by looking at the overall circuit. Remember, we've got a battery here that's supplying this, that's what's powering this. We've got the back EMF of the motor, and then we've got some internal resistance. So here's my battery, comes around, and then I've got some resistance in this circuit, and then I've got my motor here, and that's going to have some voltage drop, this back EMF, and then I continue back here to the battery. Okay, and this is the direction of the current. And then this motor, of course, is powering a shaft, which is going to be rotating at some speed omega, and that's the whole point here, right? It's like powering this battery and using this sort of clever trick with a DC motor by switching effectively the direction of the magnetic fields. I can get this thing to rotate and get some mechanical power out. Okay, so if I just do this sort of circuit diagram here, I can see that the voltage in my battery, that's the positive, has got to equal the drops that occur across the circuit. And one drop is going to be my resistance. Remember from physics, right? V equals IR, so I get that voltage drop across my internal resistance in my circuit. And then I have also the drop across this motor, that's that back EMF. All right, so I need to put those two things together. Let's see, can I add a page here? I'm going to try and add a page because I'm running out of space here. Okay, so here we go. So let's write down those two equations again, or sorry, three equations. This one, and this one. So we have that omega equals, I forgot it, omega is kV times our back EMF. Torque is 1 over kV times current minus our no load current. And from our circuit diagram, our battery is equal to our back EMF and the resistance loss. Or in other words, we need the battery to supply enough voltage to overcome the back EMF and resistance. So let's just recap where we're at here. Yeah, in this first equation here, well, this is where we started, was with the second equation here. This is the Lorentz force, right? That a current moving through this field is going to generate the force. That's the torque. That's going to be moving this thing around. But because we've got a current moving through a magnetic field, and the faster it does, or because it's moving through a magnetic field, at some rotation speed, we're going to get a voltage drop. And the faster it rotates, the bigger that voltage drop. These things are put in a circuit. My battery needs to overcome that voltage drop across the motor and any internal resistance in the system. Okay, so we have all the equations we need to solve for all the things in here. So let's just see, let's do it this way. Let's take this last equation here and solve it for the back EMF. So Vm is equal to Vb minus IR, and I'm going to substitute that in up here, and I'm going to solve it for current. Okay, so I substitute it in there, and I'm going to solve it for current. I'm just going to do this in one step here. Current is then equal to my battery voltage minus omega kV times 1 over R. All right, so the things that are going to be known, if I have a motor, once I choose a motor, we have what are called the motor constants. It's going to have some kV, it's going to have some resistance, and it's going to have some no load current. Okay, and for my battery, once I choose a battery, I'm going to know its voltage. Okay, so in this equation here, resistance is known, that's a property of my motor. kV is known, that's a property of my motor. Vb is known, that's a property of my battery. Along with my throttle, as we'll see, we can of course change that voltage of the battery, we can throttle up and down. So this tells me I have a relationship between current and my rotation speed. Okay, so there's just really kind of that one input there. Once I know my current, so let's say I just choose a rotation speed as an input, I can get the current. And then once I have the current, I can then solve for the torque, go up to this equation here, right? kV is known from the motor, I naught is known from the motor. I just calculate current, I get torque. Okay, so now I have torque, and then I can get power. So what is power? Remember power from elementary physics, we learned that power is like force times velocity. For an angular, a rotating device is going to be an angular force times an angular velocity. So power is torque times omega. So now we have both of those things. And then finally, we want our efficiency. The efficiency of my motor is going to be power out over power in. Power out, this is my mechanical power out, torque times my rotation speed. And what was the power in? Well, that's coming from my battery, right? I remember power, it's going to be IV here. So that's going to be I times my battery voltage. Okay, so that's the power in, or yeah, that's the power that I'm putting into the system. So that's my efficiency. So again, to recap, once I choose a motor and battery, I have these constants, and then I plug them into these equations. Right? First I get my current, from my current I get my torque, from my torque I get power, from power I get efficiency. So now I can compute all the properties that I care about for a motor. What does the torque curve look like? What does the power curve look like? What does the efficiency curve look like? Okay, so here's an example. And you can go compare this to yourself later if you want to run through some of these calculations, see if you get the same thing here. These first three are from a motor, so I chose a motor. I can just look up these properties from the motor, or I can determine these. And I chose a battery, or at least a battery level, or I can slide up and down how much of the voltage of the battery I'm using. But for these properties, then I get this torque curve, this power curve, and this efficiency curve. All right, so just briefly to think about some intuition here. Efficiency shouldn't be too surprising. Most efficiency curves are going to look something like this for most devices, meaning, of course, less than 1. They're going to be 0 at endpoints, right? And they're going to have some increase and decrease. There's almost always some sweet spot somewhere where if you go too far to one end or the other, you lose a lot of efficiency, but there's some point somewhere in between where the efficiency peaks. Okay, power, remember, is going to be torque times omega. So these two are kind of related. So let's first look at the torque. Why does the torque drop like that? Well, we have to go back and think about the equation. Remember, we've got this battery here, right? It comes around, resistance, and there's a back EMF here. There's kind of this trade-off, right? Because battery has got a power, oops, sorry, this one is motor. Battery's got a power back EMF of the motor and overcome this resistance. Remember from the equations that we just talked about that if I want, let's say I increase omega here, right? So I increase omega. As I go up in omega, what does that mean? That means my magnetic field is changing faster. So that means that back EMF is going to go up, right? Because I'm getting more of a changing magnetic field, right? From Faraday's law, that means that back EMF, that potential drop is going to be larger. So that's going up. So for a fixed battery level, that means I'm going to be pulling less current. And if I'm pulling less current, remember, the torque that I generate is proportional to that current. Right? As I move through that current, it's kind of that current crossed into the magnetic field that creates that torque. So if I have less current, I'm going to have less torque. So if I need to go faster, then that means that's going to be a trade-off with this less torque. And from the equations that we looked at, that's exactly linear based on our assumptions right on this constant magnetic field and such. For a real motor, it's not exactly linear, but it's going to be quite close generally. That is generally good model. So again, we're ignoring some high order effects, but it's generally very close to linear. So if the torque is linear, right, we could just write that as an equation. If you plug it in, you'll see exactly what it looks like, but it's going to be something like, let's just write the equation of a line. A plus, now let's do it like in our normal, we're used to saying like mx plus b, right? So let's just write like that, m omega plus b, right? The equation of a line. In this case, m is negative, right? Because there's a negative slope. So if we took that torque and we plugged it into here, right? Torque is here, then I would get something like m omega squared plus b omega. And this, as you can see, is a quadratic equation. So we should expect, and remember m was negative, right? M was negative. So it's an upside down parabola, just like we see here. And in fact, the peak of this, because the power is really just the integral, right? It's torque omega. So you can think of it as an integral, or the area under this curve. That's maximized at exactly halfway between where this crosses the zero line. So right here in the middle is where the power peaks, where you use the most power. That's really just a side note here. All right, so this is just trying to give you some intuition. Motors are maybe a little less intuitive, at least for me, as compared to the propeller side. So you have to let that sink in a bit. Let's talk about propellers. Try and dig into this and see how we can understand a propeller. Propellers, we're not going to get into, say, the aerodynamics of predicting how a propeller behaves. If you take the aerodynamics class, we do get into that. But what we're going to do here is instead look at some data for propellers and try to learn how to use that data to choose an appropriate propeller. So we're going to do this by looking at this data site at UIUC, University of Illinois at Urbana-Champaign, has a nice website with a bunch of propellers and some tabulated data. And we're going to find a bunch of propellers. We're going to have two numbers, and those two numbers are going to be the diameter and they're going to be the pitch. Okay, so the diameter is self-explanatory. That's going to be this. If we take this rotor area and make a circle, right, it's going to be that diameter. The pitch, you could think of it, it's kind of like the same idea with the screw, right? If you put a screw through wood and it twists, a pitch is going to be basically related to, if I do a full rotation, how much does it move forward? Right? It's kind of the same kind of idea here, that the pitch of the propeller is going to be related to how far it would move as it rotated around if it was like moving through a solid object. Anyway, it's kind of related to that. So the things that we're going to find here is a bunch of aerodynamic data. And as you wouldn't be surprised to hear, based on what we've been talking about, it's all going to be non-dimensional data, right? So we're going to have thrust coefficients, that's what this CT is, power coefficients, things that are normalized. And they're going to be functions of normalized or non-dimensional data. Maybe things like the Reynolds number, the Mach number. Mach number isn't going to get too high, so this isn't going to be relevant. The Reynolds number, as we'll see, it does matter, but the variations are not going to be too large, so we're not going to worry about it. So it's basically going to be just a function of, for a given geometry, this parameter J that we'll see in a second. Okay, so let's actually go to that site. Let's see, I'm just going to, I don't have it pulled up here, so let's just search real quick. UIUC propeller, if I could spell. Here we go. Okay, so here we go. This is the propeller data site. There's several volumes of data, but let's just first look at some of these pictures here. They're showing three things. One here is a thrust coefficient. That's what CT is, thrust coefficient, as this function J here. There's a power coefficient, also as this function J. And then there's an efficiency, it's a function of J. Efficiency, right, again, kind of has that typical behavior where it's going to have some peak somewhere, right? There's going to be a trade-off where you don't want too much or too little. So what is J? J here says V over ND. So V, that's my forward speed. So as this propeller is moving through the air, let's go sideways, moving through the air at some speed V, or it's the speed my aircraft is flying at. Or if you're in a wind tunnel, right, the opposite, the propeller is moving, it's that incoming speed, the free stream speed. ND is, you can think of this way conceptually, it's not exactly that because of just a convention, but my tip speed of my rotor would be omega times R, right? So it'd be the rotation speed times my radius. So this isn't exactly omega R, but let's think of it conceptually this way. It's a ratio of my forward speed to this rotation speed, how fast the blades are rotating. So forward speed versus rotation speed. Not exactly that again, because it's using D instead of R, and it's using this N, which to me is kind of an unfortunate choice, but it's convention. It's not RPMs and it's not radians per second. It's somewhere in between. It's revolutions per second, as we see right here, revolutions per second. So just be careful with that. Again, not revolutions per minute RPM and not radians per second, maybe a standard SI. It's halfway in between revolutions per second. Again, this is just a convention. It doesn't really matter. It's just a proportionality constant, but this is how we define what's called the advance ratio. So this is an important non-dimensional number. Again, relates my forward speed to rotation speed. That's the biggest thing that matters here. And you can see these two numbers here. These are different Reynolds numbers. So there is some change in Reynolds number. But for the propellers, we'll see in a minute, we'll find that this variation is generally not too big. This is a big range, right? This is going across 2 orders of magnitude. We're going to be looking at relatively small differences. So the Reynolds number won't be a major factor. It'll just be really advanced ratio. Okay, so we can see how some of these things are normalized. Again, these are different from maybe how we've been looking at some of the other force coefficients. This is not dynamic pressure, it's just normalized a different way, even though this is a force. Again, these are just conventions. So this is a density, this is again that revolutions per second, and D is a diameter. So just have to get used to these. You know, you may not have these memorized, so you may have to refer back to here, which is fine. There's a thrust coefficient, power coefficient, torque coefficient, and you can see that power and torque coefficient are just related by a constant. And then efficiency. Efficiency is going to be this is different from the motor efficiencies. The motor efficiency was power out, which was torque times rotation speed, divided by power in, which is from the battery. So we went from battery to rotational power. Here, my efficiency is from my linear power relative to that rotation power, right? So we're going from this rotation. But the power I care about of the propeller is how much I'm moving forward. That was the whole point of this propeller, is just creating this thrust, right, to move me forward. So this is my thrust times, force times the velocity, thrust times my flight speed. That's the power out that I care about from a propeller, divided by that power in, which is the same as the power out from the motor, right, the torque times omega. Okay, so let's dive in and look at some of these. So here's volume 1. These are just different propellers. There's a whole bunch of different names. Notice I've got these 2 numbers again. Remember what these are. The first number is a diameter, and this is in inches. And then the second one is the pitch. So let's say I pick this first one here. I've got the main ones I care about. I'm not going to worry so much about the static ones. That's going to be hover cases. But this wind tunnel on, that's my forward flight speed. I've got this first one, eta, that's efficiency. So here's my efficiency versus advance ratio. And I can see that this has been done at a few different RPMs, or a better way to think about it, it's been done at a few different Reynolds numbers. There is some variation, but it's not super large. Thrust coefficient here, similarly, right? I can see thrust coefficient as a function of advance ratio. And then finally, power coefficient. And that one you can see there's very little variation between the different Reynolds numbers. If you wanted to get specific numbers, then we got to pick one of these RPMs. Maybe corresponds to Reynolds number. Like I said, it won't be too different, so you might pick something in the middle. And I've got these tabulated data, and these are things we'll use later. These are just those same plots, just in tabular form. It'll be convenient to have actual data. Okay, so let's go back and look at some of these, and then we'll do an example. So these are the kind of plots that we'll see, just like we saw. I'm just plotting them together: thrust, power coefficient. But what we want to look at now is, although non-dimensional data is of course very important and more useful if I'm tabulating these things, right? Because they're going to be universal. I want to look for my specific propeller, and I need to know if I have enough thrust, right, to overcome drag. That's not non-dimensional. And I need to know like that my torque is going to be a match for my motor. So I need to figure out these dimensionally. So let's do that here with an example. Let's try to work out an example. I'm going to do this here on the fly, so hopefully this works out all right. Let's see, the example we're going to do is, we're going to use the slow flyer. This is an APC propeller. Slow flyer, 8x6, so 8-inch diameter, 6-inch pitch. It's going to be flying at 10 meters per second, and we're going to say rotate at 10,000 RPM. Okay, and so my goal here is I want to figure out the thrust. Let's just say that. Let's just figure out how much thrust do I produce. Okay, and that might be useful to know because I need to know at this given speed. I know what my drag is. We've kind of worked out calculating drag from airplane. Do I have sufficient thrust, okay, to overcome that drag? So let's try and do that. So let's go back to that website. Okay, so I said this was an APC, so I can click on the APC link here. Here's the slow flyer category, and let's go down 8x6. That's this one right here. Oops, 8x6. And I'm going to look at the thrust coefficient. Here's my thrust coefficient, and notice it's a function of advance ratio. Okay, so I need to figure out what my advance ratio is. So let's go back. So advance ratio is V over ND. V I have, N is in rotations per second. Okay, so that's going to be, say I've got rotations per minute. So I need to divide that by 60, right? So let's see, rotations per minute. Yeah, divide by 60. So that's going to give me 166 point, just round it here, rotations per second. Okay, and D is my diameter, and that is this number right here, right? 8 inches. But I don't like working with inches. I like to stay in metric units, and my speed is already meters per second. So let's see, 8 inches to meters is 0. I'll just round it here, 20 about meters. Okay. So let's plug that in. What's my advance ratio? It's 10 divided by this 166.7 times 0.2. It's about 0.3. Okay, so my advance ratio is 0.3. All right, so let's go back to that graph. And that corresponds to, let's see, about, can't really use a laser pointer here, I don't think, on this website, but it looks like that's a thrust coefficient. I'm just going to pick somewhere in the middle of all those curves, about 0.13. So this is 0.1, yeah, about 0.13. So from my graph, that gives me a thrust coefficient of about 0.13. All right, but remember I need thrust. So to do that, let's go back to the website and look up, what was the definition of thrust coefficient again? I'm gonna go back to that main page. Here it is. Okay, so thrust is gonna be thrust coefficient times rho times n squared times d to the fourth. So thrust is CT times rho times n squared times d to the fourth. I already have all of those except for rho. Rho is, you know, going to be 1.1, 1.2, or whatever, depending on your altitude here in standard SI units, right? Kilograms per meters cubed. So let's plug all that together. So I've got a CT of 0.13. My N is and actually, so here I got to be careful. I need to do this in radians per second. So I'm going to convert that because that's going to be my standard SI units. I put this all together. So let's see, 0.13 thrust, the conversion from RPM to radians per second. I square that, and then I multiply it by diameter, fourth, and then let's say a density of 0.1 or so. And if I did all that right, I should get, oh, sorry, no, it is N. I'm going to do N. I don't, oh, let me fix this real quick. 166.7, yeah, so sorry, I misspoke about omega, I forgot. This is actually N, right? So it's in rotations per second. So I got 0.13, my density, just to keep it simple, we'll just say is, I don't know, what is it around here, like 1.05 or something like that. N is 166.7, I square that, and then take D, which is 0.2 to the fourth power, and I get about 6 newtons, okay? So, yeah, about 6 newtons of force. All right, so you can try that on your own to see if that makes sense. So let's look at this from that example. We could repeat the same thing, and this is, of course, we did it by hand. It'd be easier to put this in a little script, so we can repeat this a bunch of times. But we can get curves just like we did for the motor. We can get a curve for my torque. I can get a curve for my power. I can get a curve for my efficiency. And of course, I get a curve for my thrust, which I didn't get from a motor, right? The motor doesn't produce thrust, the propeller does. Let's see what those are going to look like. Actually, I didn't draw them here, so I'm just going to draw them real quick on this slide. This is the torque one. This is omega. For a propeller, the power is also going to go up. Right? It's going to go up like this. Efficiency, we saw, is going to kind of come up and down. And the thrust is also going to kind of go up like that. So I guess these are a little bit more intuitive. Maybe that's the way to draw. It's kind of what you'd expect. As you rotate faster, that's going to require more power, produce more thrust. And torque is, of course, related to the power. So they all go up. But here's the key sort of finishing thought here. I now have all these curves for my motor and my prop. And then the question is, so what? When I put the motor and prop together, they're going to operate as one unit, right? The whole point of my motor is that I'm fitting the propeller onto the shaft, and that motor is driving the propeller. That's what's causing this to spin, right? The battery is providing an electric power, which is being converted to rotational motion in the motor, and then that's driving the propeller, and that propeller is converting that to a linear power as I move the aircraft forward, okay? But the motor and the prop, because I put them together, they do not operate independently. So I've got these two curves here, rotation speed, the motor, remember we saw how the propeller is going to drop in torque as we increase in rotation speed, because the propeller is going to increase. And the question is, well, this combination, what do they operate at? The answer is where they intersect. If we think about that, that should make sense. If I put these together, they need to spin at the same rate, right? The shaft is what is spinning the propeller, so they better be spinning at the same speed. And they have to have the same torque, right? I mean, that's what's driving it. The torque of the motor is driving the torque of the propeller. That's like saying, if I push on the wall with some force, the wall is pushing me with that same force. That's the same idea, right? The motor is providing this torque to the propeller, so that's the same torque. Of course, that wouldn't be true if I was slipping, right? If I had a really bad fit, this thing was spinning around, that would be kind of a useless propeller, but assuming it's not slipping, it's on there, those torques are equal. So when I choose my motor and my propeller, I do not get to choose the speed that it rotates at. It is dictated by this combination. Okay, and of course I can change that as I change the voltage that's going across the motor, for example, where I can slide this curve around and then get a new intersection. Or as I fly at a different speed, for example, then this propeller curve may shift, right, and then get yet another different intersection. So I can move these things around, but in short, whatever I'm operating at for my propeller and motor, those things are are determined, right? Once I decide voltage for my motor, I decide the motor properties, and I have the propeller, I know what speed I'm flying at. The rotation speed is determined just by those equations, right? I don't get to choose that. It's not a free parameter. That's chosen indirectly, as we see kind of from this diagram. Indirectly, this is kind of an indirect function. So just to say it this way, propeller, we could say, well, it's omega and my speed for a fixed propeller, and my motor, it's got omega and my voltage. But these two are not independent because we have to figure out where they cross. So that rotation speed is really dictated by my speed and my voltage. So as we'll see, next time we'll talk about this a little more. Of course, I can change my voltage or my flight speed around, but that's going to kind of dictate my omega. So we're going to talk more next time. How do I choose an appropriate motor and propeller to give me a good overall performance? Okay, so we'll see you next time.